It's great to see so many people come out. I was almost hoping for rain today. My name's Jim Powell, and I'm an assistant professor here at UAS, and I currently lead the Master of Public Administration program. As Alaskans, you guys know that there's climate change happening all over. Villages are eroding away on our western shores. There's thawing permafrost, and there's changing fish runs. We know it well. So it's a special honor and a pleasure to introduce Dr. Don Wuebbles as our speaker tonight. Don is one of the top climate change experts in the world. Dr. Don Wuebbles is also the leader of the report that you're seeing up here, which is the fourth iteration of a national report on national climate change assessment. So he's also an atmospheric scientist. He does assessment. This guy knows data well. He has over 500 publications, and to us academics, that's a big number. He's also a recipient of the Group Nobel Prize, Peace Prize for the 2007 International Panel on Climate Change report. And he also was the advisor to President Obama on climate change. So when he wanted to know something, he called Don. Anyway, the reason why he got here, just a little, and I want him to speak, of course. When my wife, Beth Gertula, who worked with Don in the White House, told me that Dr. Wuebbles and his wife, Barbara, who was here tonight and stayed with us this week, was coming to visit, I had to ask him to speak, so that's why he's here tonight. We are indeed fortunate to have such a distinguished scholar with us, and I know we'll learn a lot from him tonight. And one other plug, tomorrow morning at 10 o'clock is the climate rally in front of the Capitol. So hopefully we'll see you there. So please help me welcome Dr. Wuebbles.
Thanks, Jim. So thank you all for being here, and thank you for inviting me. What a beautiful library. I'm really jealous of all this artwork you have here. It's just gorgeous. What I'm going to do tonight is tell you a little bit about the science of climate change. As Jim mentioned, I was lucky enough to be asked to lead the scientists that reviewed and assessed the state of our science from around the world, all the published literature, in terms of what impacts are happening on the Earth's climate system and what that means especially to the United States. I'll try to focus in especially on Alaska as I can. We had one chapter of the assessment that dealt entirely with Alaska and the Arctic. But I, of course, won't have time to go in great detail. What you see on the cover page is the front of the executive summary from the assessment. It's the only part of it we've actually published in print because the full 475 pages is actually available on the web. I'll point you in a minute to the website. What's on the cover actually is a very interesting photograph taken from a satellite of what's called an atmospheric river. And this brought a huge amount of rain into California and brought it, at least temporarily, an end to the drought in California in, I think it was 2016. So just to start with, I thought I'd just mention, I'm sure you're probably all aware of this, there was a very contentious vote related to climate change in 2016. Particularly August 16th, 2016, the people of Shimmeref decided that they were going to have to leave their homeland and move. It's one of the very first events worldwide where we've seen people actually having to move because of the effects of climate change. In this case, because of the decrease in sea ice, as I'll show you, we've had about a 40% decrease in sea ice in the summer months. In the Arctic, that's resulting in a lot of wave action affecting coastlines up there and having a huge impact. So that really brings it home that climate change is affecting us. I'll talk a little bit more about that later, that climate change is in fact affecting all our pocketbooks in many different ways, and we just don't tend to realize it. So even those, most people in the US, I would think, say that, climate change may be happening, but it's not affecting me. Well, it is affecting you. If you pay taxes, it's affecting you. So having Americans become climate refugees was kind of startling. So back to the assessment process. Every 4 to 6 years, both internationally and nationally, scientists are asked to come together to assess the state of the science in terms of what it means in terms of the effects of climate change. What is happening, why is it happening, and what is happening to society and ecosystems as a result. I've been lucky to be asked to be a lead author on a number of the different international assessments, including the first one in 1990, and also this most recent one in 2013. The sixth assessment is currently started. This was the fifth one. And it's a whole lot of work, and you don't get paid anything for it. This is all pro bono when the scientists get asked to do this. We do it out of service to our society, to service the society. Well, in addition to that, in 1990, the US Congress passed the Global Change Act, signed by President Bush, the first President Bush, and and what this does is it requires that there be an assessment of what is happening to the United States in terms of global change. It was intended to be every 4 years, but it was quickly forgotten, and it wasn't until various presidents were sued that we finally started doing it every 4 years ago. And now, starting in 2009, we finally got our acts together. We had the second, third ones in 2009, 2014, and now this was in 2017 for the first volume. The second volume will come out this year, which looks at the impacts on society. So this was the third assessment right here. So I'm going to talk tonight about the first volume of the fourth National Climate Assessment, which relates to the science of climate change. So I'm primarily going to just talk about science. And it is available on the web, science2017.globalchange.gov. And if you look there, you will see the full 470-some pages of the assessment. You can see copies of the executive summary, which I understand there are copies available here for you all. I brought a few with the fancy, pretty cover, but I don't have very many with me. There were 51 authors in total. We had 12 federal agencies involved. We had a federal steering committee that kind of oversaw the thing, that chose who would be selected, making sure they were quality scientists who would do a good job with assessing the state of the science. And then we went through a whole series of reviews. I think this said 5 reviews. Well, the 5 reviews was before the final review, which was when it was finally signed off through the White House by the agencies. But the 5 reviews included multiple reviews by the 12 agencies, plus a public review where scientists could also review as they wished. But on top of that, we had a special review by the US National Academy of Sciences. And so it went through probably the most reviews that any scientific document has ever gone through. And yet we managed to get it approved in 2017 and out there towards making a difference. Well, what does it tell us? This is the bottom line. Our climate is changing. It's happening right now. People always tend to think climate change is in the future. I don't have to worry about it, right? No, it's happening right now, and I'll show you some of the evidence for that tonight. It's happening extremely rapidly. In fact, it's about 10 times more rapidly than nature tends to change the climate. Climate has changed in the past. We know that very well. but it's primarily changed because of very slow moving activities. Changes in the sun, changes in the amount of carbon dioxide in the atmosphere back millions of years ago because of outflows of CO2 from volcanic eruptions. Now that doesn't happen. Most of the effects of volcanic eruptions now are the sulfur that they put out and cause a cooling effect. And this changes in climate are leading not only to a warmer Earth, but it's having much larger impacts. You'll hear the media talk all the time about global warming. Well, it's funny because as a scientist, I've always called it climate change, and most scientists do. We'll call it global warming because that's the term that's out there in the public. But I get accused of changing the term from global warming to climate change because I have something to hide. I don't know what that is, but apparently it's out there. But it was actually the media that started using the term global warming 15 years ago or so. But it's so much more than temperature change. It's the changes in severe weather that are happening. And in fact, I do a lot of my research is related to how severe weather is being affected by the changes occurring in our climate system. It's making certain events more intense. On top of that, sea levels are rising, which are affecting our coastlines and are going to likely have a very significant effect on coastlines over this century and perhaps very likely beyond that. Why is this happening? It's happening largely because of human activities, namely the burning of fossil fuels, land use change, both of those contributing to, and it's other pollution aspects, but primarily those two, that contribute to increases in the amount of carbon dioxide and methane and some other gases in the atmosphere that are there in rather small concentrations, parts per million of concentrations. Means one molecule per million molecules of air. How can that make an effect? It's because those gases absorb radiation in what's called the greenhouse effect, absorb infrared radiation that otherwise would go to space. And this would be, if it wasn't for those gases, this would be a frozen planet. But because of those gases, we have life as we know it. But what we're doing is we're adding to the amounts of those gases. And that's really affecting the Earth's climate. If you go look at the basic physics, it's rather surprising how simple the processes are. It's very complex to look at the actual rate of transfer and all that aspects, but just the basic concepts are quite simple. Our climate will continue to change over this century and probably beyond because we can't slow this down quickly enough. But we can have a large impact. I can easily leave you very depressed by the end of the evening by showing you everything that's happening. But I don't want you to be left that way. I want you to realize there is hope, that we can do something about this, and hopefully you'll see that as we go through this. Well, we have lots of different observations. Since the last assessment in 2014, we've had millions and millions and millions of new data that tell us that the climate is continuing to change very rapidly, and all the other things I told you. And it's not just temperature or land surface temperature or sea surface temperature or even tropospheric temperature, but it's the amount of heat in the oceans. 90% of the heat, the increase in energy that's happening because of the increase in these greenhouse gases is ending up in the oceans. And it's having so it's kind of keeping us from having much worse climate change than would have happened otherwise. The oceans play a big role because they have a large heat capacity. Water vapor, specific humidity, is increasing in the atmosphere because as the atmosphere warms, it can hold more water vapor. It's basic physics that it should be able to do that. In fact, that's what's happening. The amount of water vapor is increasing. Snow cover, most of the glaciers in the world, not all, but vast majority, well over 90% of the glaciers in the world, and things like sea ice extent are decreasing throughout the world. An indicator of the warming temperatures. If we look at the global temperatures and the many, many thousands of observations made each day by thermometers, basically, well-controlled thermometers, and we put this on a relative scale because There may be some uncertainty in the absolute temperature, but we can knock that out by just looking at the changes over time. We see that the temperature since about 1900 has increased by 1.8 degrees Fahrenheit. Well, that may not sound like much. 1.8 degrees, we get more than that in a daytime, right? From night to day. But we're averaging over every day, over all parts of the Earth, and that's a thing that should vary very slowly. In fact, if we go back further in time, as I'll show you shortly, you see the temperature changed very, very little for thousands of years. But now it's changing quite rapidly. So 1.8 degrees is large. If you go back and look at the last ice age, it was about 15 degrees Fahrenheit colder than current temperatures. Well, that's when we had ice covering most of the area. Well, certainly the area where I live in the Midwest was totally covered with ice. And so that was really big impact. So 1.8 degrees is over 10% of that effect, and that's not negligible in terms of an impact. If you looked at every decade, look at those temperature changes over a decade, every decade for the last 5 decades is getting larger. We're going to see that again this decade because as I'll show you shortly, the recent years have all been extremely high. Go back in time, taking that temperature record and go back 2,000 years now by using proxies for temperature, in this case for the Northern Hemisphere where we have the best data, you can see that the current temperatures, the red here is that same distribution I had before, the current temperatures are much higher than anything we've seen over the last 2,000 years. But yet, if you look at that temperature record from the proxies, you can see the medieval warm period. That's the period when Vikings were living in southern Greenland. You can see the little ice age when it was colder than normal in much of North America and Europe. And which we think primarily was due to large volcanic eruptions, by the way, which caused an effect on the oceans. Not because there was a modern minimum of very few sunspots, because we don't think that has much effect on the solar flux. Now, if we looked at going back to that record over the planet and look at it across the planet, we didn't have observations in the Arctic or Antarctica going all the way back to 1900, so that's why they're gray there. We just didn't have data. We do have enough data to know that the Arctic has increased at twice the rate of the rest of the world, and I'll discuss that in a second. But if you look at this, you see the largest changes have occurred over land. The oceans have a large heat capacity. They respond slower. The land is where we're seeing the largest effects. It's also where we're seeing these really large effects from severe weather, particularly this year. It seems to be a really bad year. There's one area up there where you can see a net cooling, and that's off the coast of Greenland, where the fresh water that's getting into the Atlantic Ocean is causing a slowing. This is from the melting of Greenland and the melting sea ice, is causing a slowdown of the Atlantic Ocean and the circulation of the Atlantic Ocean. And that one little area there is actually cooling slightly as a result. There's the one other area, and it doesn't show very well on the slide, that shows somewhat of a cooling is actually in the southeast United States. And I'll talk more about that shortly. Oh, by the way, 2016 was the warmest year on record. 2017 and 2015 were essentially tied for second. And both of those years far surpassed 2014, which was the third warmest year on record. Then 2010. 17 of the last 18 years are the warmest years on record for our planet since we started taking observations in the late 1800s and getting global representation. The one exception, by the way, was 1998, which happened to be a strong El Nino year and barely beats out one of the years after that. But it was really unusual. So we're seeing extensive warming of our planet. If we look at the United States, you can see that the southeast is some areas of the southeast have a slight cooling. Sometimes I would joke that that one of the largest areas there happens to be near Huntsville, Alabama, where some of the largest deniers of climate change live, and so it dare not warm there. But reality, we think it's more likely because of the deforestation that occurred in the Southeast in the 19th century, followed by the reforestation in the 20th century. But it could also be related to some of the changes in circulation patterns, weather patterns that have also occurred since then. But there's definitely been a small cooling. Actually, if you look at the Midwest in certain seasons, such as the summer, spring and summer, we've actually had a cooling somewhat in the Midwest. There we know that it's related to increases in soil moisture from the increase in precipitation we've had in the Midwest, which is helping keep things a little cooler than it would have been otherwise. So if you look at precipitation patterns overall, which is the right-hand side here, annual and then by season, we've seen about a 7% increase in precipitation in the United States, but it's not distributed evenly. Basically, we've seen a drying of the West and the Southeast, and a wettening of the Midwest and the Northeast. And Alaska is kind of mixed. Some areas increase, some areas decrease. Looking at the Arctic, it's really the place where we see the largest changes on Earth. So you sit at the front line, or sometimes we call it the canary in the coal mine. Temperatures warming at twice the rate of the rest of the world. We're seeing an accelerated melting of multi-year sea ice cover. We'll talk about that more in a second. We're seeing a significant mass loss from glaciers, including those on the Greenland ice sheet, reduced snow cover overall, and perhaps most important, perhaps to the rest of the world, as well as to Alaska, is the permafrost melting, down 12, 20 meters in a number of places, where this melting over this century not only will increase the temperature and cause potential infrastructure effects, as it's occurring already on roads and buildings, but could release methane and carbon dioxide into the atmospheres that would further add to the overall warming of our planet. It's one of those great tipping points that we don't understand very well, that is kind of a scary thing. People ask me, what keeps you up at night about this problem? Well, that's one of them. That permafrost melting is important. And my wife will be happy to tell you that I'm up a lot on ice. She's always giving me a hard time about it. So if you look at chapter 11 in that report, one of the key findings is that we are seeing a much more significant increase in temperature in the Arctic than in the other parts of the world. And if you look just at Barrow, and I could try to say, I know I'll get it wrong again, Utchivik, Alaska, it's 3.8 degrees centigrade. It's about twice that Fahrenheit in September. Almost 7 degrees in October, 5.5 degrees in November. Again, it was all in centigrade. We're seeing an increase in that part of the world of more than 1 degree centigrade per decade overall. It has been very dramatic and is having a significant impact in those regions. I'd mentioned the permafrost melting, and it just shows some of the data taken by scientists since the 1970s, showing this overall an increase in the amount of melting of permafrost. If we look at I'm going to try to show you a film here. Shoot. It's hard to see on this little screen. There it goes. So this starts in 1984 and goes through 2016, I think it is, showing you the thickness of the ice in the sea ice and the overall extent. Overall, we've seen a 40% decrease in the overall extent over this time period, and that's equivalent to the size of Alaska, plus the size of Texas, plus the size of California, plus the size of Missouri. So very extensive amount of sea ice has been lost. And this shows 2016. And you can see how much of that is new ice, you know, the very thin ice. And it's getting to be more and more like that. Now, the last few years have not changed this very much. And that's in part because we're seeing effects of other man-made pollution, putting aerosols in the atmosphere, which cause a cooling effect, and are keeping the ice from melting even more than it would have over the last few years. But in general, if we look at, again, decadal timescales, which is the timescales we start talking about climate change, we really talk about 20, 30 years is the time for climate. Weather's what you get. Climate's what you expect. That's based on a quote from Mark Twain. So this just shows that on top of all that, the ice melt season has also lengthened by 20 to 30 days over those last 40 years. And so it's not just that the fact that the ocean's warming, it's that the overall seasons are changing as well. Now we can look also, let's see if I got another little film here, looking at Greenland. Oh, come on. There we go. So what this shows is the ice loss over Greenland. And we've seen about 2.81 gigatons of ice loss every year. This is equivalent to about 140 million Olympic-sized swimming pools being lost every year in terms of water off of Greenland. So far, it's had a pretty small effect on sea level rise, accounting for about a quarter of the sea level rise. But the big concern is what will happen over this century as this ice continues to lose. So what this just shows is how much equivalent is being lost relative to 2002. This is based on the GRACE satellite. It's one of the wondrous satellites from NASA that can measure the gravity and from that determine the amount of ice that was there over time. Barbara and I took a cruise 6, 7 years ago, roughly. What? More. I never remember anything. And when we did, I was shocked to find that when you get to Glacier Bay National Park, that all this area that this big, huge cruise ship had gone up to so you can see the glaciers calving, was in ice in 1941. Really indicates that, you know, the kind of dramatic change you've seen here in Alaska. And one of the findings of the report was it is very likely that human activities, very likely is our code word for greater than 90% likelihood, that human activities have contributed to observed Arctic surface temperature warming, sea ice loss, glacier mass loss, and northern hemisphere snow extent decline. It's a high confidence statement. But I felt we were almost being too weak in saying it contributed because it's largely causing those changes. It's always funny, I always get approved of being an alarmist, but in fact, scientists tend to be pretty conservative in our statements. And so for us to make some of the statements you'll see here, some of which are fairly strong, there'll be some more in a minute, means we've really learned a lot about what's going on. And it is human activities, for example, that is driving what we're seeing. One of the most interesting things that is happening is that changes in Arctic sea ice, particularly, and the changes going on in general in the Arctic, appear to be driving some changes going on at mid-latitudes and over the rest of the United States and over parts of Europe that we're still trying to understand. Jury's still out on this, but we think that this changes in circulation patterns, the fact that the jet stream seems to have much larger waves in it than it used to, much larger extent over latitude than it used to, and leading to some significant weather in the Midwest, for example, or the mid-latitudes, is related to what's going on in the Arctic. And we're still trying to understand that, but it seems to be the case. And very interesting questions there about what is going on and how the Arctic is really influencing the rest of the world. It's a little bit like the tail wagging the dog, because the amount of mass of air in the Arctic is smaller than those areas outside the Arctic. But some very important things going on here. Well, looking beyond temperature change and some of these other things going on in the Arctic, and looking at extreme events, we're finding extreme events are increasing throughout much of the world, and including the United States. One of the ways we know that is since 1980 for the US, and roughly the same time period worldwide by various reinsurance companies, actually, people have been evaluating what are called the billion-dollar events. These are events that cause $1 billion of effects in infrastructure. Nothing about human lives, just infrastructure. And it has to be $1 billion or more. So if it's only 900 million, it doesn't make the list. It used to be when they started doing these, we would have 2 or 3 such events per year. That's those bars coming up. And in some years 4, maybe 5. Now we are typically getting well over 10, typically more like 14, 15, 16 such events per year. For example, we had, I think we had 16 such events in 2017, which isn't shown on here. We had one less than that in 2016. 2017, in fact, was the warmest, was the year that had the largest impacts on American people. This is just for the United States. And so we're getting many more of such events. They're not all related to the fact that more of the population is moving to coastal areas. It's not just hurricanes. I can show you the same thing without hurricanes, and you're still seeing the same effect. But you're seeing effects throughout the United States. And the net result is that we've had a total of $1.5 trillion impact since 1980 to the American taxpayer. So this is part of the proof that climate change is affecting your pocketbook and mine. Now you could say part of that was natural. Yeah, it was. But the vast majority of that increase is related to the fact that the climate has changed. Well, what kind of changes are we seeing? In the United States, since 1960, we've seen an increase in the number and severity of heat waves. Worldwide, it's been since 1900, but in the US, we had the period of the 1930s when we had the period, particularly out west, where we had significant warm events. And so, but since 1960, we've seen a fairly steady increase in the United States. Cold waves are decreasing. So, that's one of the, I guess, good things, and that cold waves, getting really bad cold periods are decreasing in number. Doesn't mean we don't get them. They do happen. We had one this last winter in Illinois. But we're having less of them than we used to have. More precipitation. Remember I told you when it's warmer, the atmosphere holds more water vapor? Well, that leads to more precipitation. And precipitation tends to come out as larger events. So when you can build up this large amount of water vapor in the atmosphere, you can dump that out as large precipitation, large rainfall, large snowfall. So sometimes people say, well, there's been, you get 30 inches of snow in DC. That must mean, as Senator Imhoff said, that there is no global warming. Just because an event happening in one place doesn't make sense. But on top of that, it doesn't make sense because we actually expect that a large precipitation events should be increasing in number. And that's exactly what's happening. I'll show you a little bit of evidence for that. As a result, we're getting increased risk of floods in certain parts of the country, particularly the Midwest and Northeast, where we're getting the particularly significant increase in these large precipitation events. It's happening throughout the nation, throughout the world, even in the dry areas. When it does rain or snow, it's likely to be a larger event than it was. We're seeing an increasing intensity of droughts. I told you the way precipitation is being shown over the United States differs by region. And because of that, we're getting more droughts in particularly the Southwest and the Southeast. Because of the drying and the warmer temperatures in the West and in Alaska, we're seeing much larger incidences of wildfires, more severe wildfires than before. Nothing about the number, but when you get a wildfire, it's more likely to be a larger one than previously, and many things that go along with that. We're seeing an increased intensity of hurricanes, particularly in the Atlantic, and that's likely to increase more in the future. Tornado activity, which is not so important here, but certainly is where I live, the jury's still out on. We don't have enough information. We have seen an increase in outbreaks of tornadoes, where you get more tornadoes. When there is a tornado, more likely to get a whole bunch of them. But the intensity has some counteracting science to it that we're still trying to sort out. One of my students recently published a paper, in fact, was just released this last week, finally, that shows that based on the very limited data we have on hail, because the data for hail, we just don't have good enough data. What we do have more recently is data from radars that tell us something about how hail is being distributed. And we're finding it's likely becoming more intense as well, based on those analyses. All of those things are likely to continue. If I look at the large precipitation events, this is from the assessment. If we look at the top 1% of the precipitation events since 1958, we've seen a 42% increase in the Midwest, 55% increase in the Northeast, and a 16% increase in Alaska. All areas of the continental parts of the United States have seen an increase. Ireland's a little more difficult because islands are so dependent on when a hurricane happens to hit them as to how much rainfall they get. And so they vary almost year to year in terms of trying to look at those kind of statistics. But extreme rain precipitation events are very likely to continue to increase, just as extreme high temperature events are likely to continue to increase. And a sad thing for me is our models are tending to underestimate the actual magnitude of these events, which makes me wonder if our models are just not good enough quite yet to really say just how bad things are going to get to be in the future. It's one of those things we're trying to understand. I mentioned wildfires. The US fire season is about 3 months longer than it was 40 years ago. And the average fire is much bigger, sometimes 1,000 degrees more, and hotter. They're not bigger in size, but also much, much hotter than before. In Alaska, even the tundra is experiencing wildfires. And I think I have a slide related to that from the assessment showing how in recent decades Alaskan wildfires activities have increased both boreal forests and in Arctic tundra. If we look at the science carefully, we can try to detect when a special event occurs. Is that related to the fact that climate is changing? In fact, we think almost all weather events are being affected by climate change, but we can go in and analyze particular events and say, well, because the climate has changed, was that event worse or better than it would have been before? In this case, for looking at Hurricane Harvey, the occurrence was 3.5 times more likely because of the fact the climate has changed, and the rainfall was 15 to 38% greater. And what was currently a 1% chance of such an event per year before the end of the century might become an 18% chance per year. So much more likely to see very significant hurricanes. What's up causing the observed changes? I've already told you about the greenhouse gases, carbon dioxide and methane. that they are primarily responsible for the observed climate changes. I don't have time to go through all the different analysis we do to make that statement, but I can tell you, this is a key finding from the assessment, that for the period extending over the last century, there are no credible alternative explanations supported by the extent of the observational evidence for any alternative. Solar output changes and natural variability can only contribute marginally to the observed changes. In fact, over the last 40 years, the amount of solar output, which we measure very carefully from satellite observations, is actually decreased, not increased. So it can't be the sun. The climate just doesn't change on its own. It changes over periods of time because some forcing has affected it. And there are no natural cycles. You often see in the media, oh, it's just natural cycles. You know, we've had the climate change before, it must be a natural cycle. No, there are no natural cycles that can explain this. Now, for having an ice age every 100,000 years, oh yeah, we have that evidence. That's because of how the sun goes, or the Earth goes around the sun. But there are no natural cycles explaining this very significant changes we've seen, particularly over the last 50 years. If you look at the amount of carbon dioxide, I mentioned this is one of the important gases, probably the most important changing gas in the atmosphere. Has an atmospheric lifetime, has a rapid exchange between the atmosphere, the biosphere, and the oceans. But the overall lifetime of CO2 in the Earth's system, and particularly in terms of if you add CO2 into the atmosphere, it's about 100 years. Its second lifetime is more like 4,000 or 5,000 years, well over 1,000 years anyway. What we've seen is a very significant increase in just what we've observed in CO2 amounts since Charles David Keeling started taking very accurate measurements in 1957. I like bringing up Dave Keeling because he was a graduate of Illinois, but he was also a very famous scientist for his work at Scripps in California. But we go back much further in time by looking at the bubbles that are trapped in ice cores. Particularly in Antarctica, we can take an ice core that goes back 800,000 years. If you see these ice cores, you can basically see every single year of these very, very long cores of ice that are about this thick. It's really amazing. And from those, you can pull out particular years, you can pull out the gas that was trapped in that ice and measure how much CO2 there was. And what you see is that when there was an ice age, there was about 200 parts per million. When there wasn't an ice age, it maybe got as high as 300 parts per million. Right now, we're about between 405 and 410 parts per million. We've had a 40% increase relative to what should be there in between ice ages. It should be driving a very significant change in the atmosphere. And in fact, if you went back to the last time we were at 400 parts per million, you have to go back 3 million years ago. And that was a much warmer Earth, with sea levels 60 feet higher than current sea levels. It's kind of a scary thing, because it's telling us, in part, that CO2 really plays a big role in affecting the Earth's climate, but it also says what could happen over the coming centuries if we don't do something about this issue. Another way of looking at the issue is to say, well, what if we look at natural forcings on climate relative to that observed temperature record I showed you earlier? And in this case, there are multiple different analyses. This just shows 3 of them, of all those observations. I showed you the NOAA one earlier. But NASA, Goddard Institute of Space Studies, also does analysis. That's GISTEMP up there. And the UK, United Kingdom, does an analysis from their Halley Center, which has had crude 4.5. And you see they all get basically the same thing. They disagree a little bit in their analysis. I won't go into all those details, but basically they get all the same effects. There's some others out there, they all get the same effects. But what if we go to the right here? What if we only consider the natural forcings? Only consider the sun. Volcanic eruptions would tend to cause a cooling because of the sulfur put in the atmosphere, turning into sulfuric acid and causing a cooling effect. Well, we find we cannot explain what's happened in the last 40, 50 years. you would have expected almost no change, whereas in fact we've had this significant increase. But if I include those greenhouse gases, I include CO2, I include methane, and nitrous oxide and some other gases that we have measured for quite a significant amount of time, and how much they've increased, we agree almost exactly with that observational record. Well, we also try to project in the future. We use our models of the atmosphere and the climate system. It's really models of the complex climate system, the Earth, the oceans, the biosphere, and land, and try to look at what can happen in the future. The current pathway we've been on is to heavily use fossil fuels. That's the highest scenario there. This scenario started in 2005 going forward, and we're basically following that high scenario at this point. And if we were to continue to heavily use fossil fuels, we would end up with a significant increase in the amount of carbon dioxide by the end of the century, even more than now, but much more than now. But we would also end up with another 8, 9, 10 degree Fahrenheit increase in temperature globally. This is globally. Well, hopefully we can do something about that, and I think we are. I think we're on the verge of a revolution, actually, in how energy and transportation is being done. And so if by mid-century we slow that down and actually decrease emissions after that by a significant amount, we could hold to this blue line, which is RCP 4.5, and maybe have more like 3 to 4 to 5 degree Fahrenheit increase in temperature. So that shows you we can have a big impact. Now we'd like to keep it below 2 degrees centigrade, and that's that lowest scenario. I don't think we can reach it, but we should try, where we very rapidly start decreasing emissions. We're seeing a small decrease in emissions now. We need to be doing something a whole lot more rapidly, though, to keep to that 2 degrees, likelihood of 2 degrees. Well, if we look at the middle, the highest scenario and then the lower scenario, 4.5, not the very lowest one, we find by mid-century there isn't a lot of difference between the scenarios. There's a little bit more with the high scenario than the lower scenario, but not a big difference because the emissions we've already made are going to cause most of the changes we're going to see over the next 20 years or so. But we start seeing some differences, and over Alaska you particularly start seeing some pretty significant differences. But if you go up by the end of the century, there's very large differences between the two scenarios. So mid-scenarios, mid-centuries on top, and late centuries on the bottom. And the largest changes with the high scenario or with either scenario projected to actually occur in Alaska. But we expect even some pretty significant changes at mid-latitudes and central part of the US, where I'm from. If we look at precipitation patterns continue to change such that we expect that the dry will get drier and the wet will get wetter. And much of Alaska is likely to continue to see an increase overall in precipitation, with more of that precipitation coming as larger events than in the past. But a continued drying of the west coast and the southeast and continued issues there with drought. And even in other parts of the US, more significant concerns about drought, particularly in summer months, including the Midwest. And I'm the son of a farmer, and I'm always worried about agriculture, so that's, I find very disconcerting. This is for late century, but it's similar effects for mid-century, a little bit smaller. Switch quickly to sea level rise. Sea level rise is accelerating as we get not only warmer oceans, water expands as it gets warmer, but on top of that we're getting this increase from the melting of ice and land ice, particularly what's happening from Antarctica and Greenland, but also glaciers throughout the world. We've already seen about 7 to 8 inches. We can expect another 1 to 4 feet of sea level rise over this century. It somewhat may depend on which of those scenarios we follow, but we're not absolutely sure of that. It could be independent of those scenarios because we start the ice changing. We may be putting certain activities into place that are going to cause it to continue to change. Because of what's happening in West Antarctica, where there's significant melting there, particularly in the ocean ice that is holding the ice in the mountains from and the glaciers there from just falling into the sea. We can't for sure say there won't be as high as 8 feet of sea level rise by the end of the century. Part of what we were trying to do in this assessment is do risk analysis, trying to say what's the risk for various likely events. So the 1 to 4 feet we feel pretty comfortable about. We don't feel comfortable yet about what's going on with West Antarctica, but we can't for sure say it won't be as high as 8 feet. On top of that, the oceans are changing in many different ways. I already told you about the changes in the circulation in the Atlantic, but the oceans are also acidifying. 25% of that CO2 that goes into the atmosphere is ending up in the oceans. As it gets in the ocean, it turns into carbonic acid. That acidifies the oceans, makes them less basic than they are. They don't have, their pH is still on the basic side, but they're getting less basic. That's having an impact already in some places on shellfish and other life. What that means in the long term to the oceans is still unclear. How that's going to affect life in the oceans. The oceans are warming, but on top of that, this acidification effect is a big concern. And there's some other effects, but I don't think here's a couple of them. Declining oxygen concentrations at some depths is also occurring along coastal areas. And that is getting to be more of a concern as well. One of the things that is happening, not so much here, but in much of the rest of the United States, is what is called nuisance flooding. This is Norfolk, Virginia, where streets in Norfolk are beginning to get flooded on a regular basis whenever there's a high tide. To the extent where and it used to be like it would last a few hours now and be a few inches, now it's lasting a few days, and it's a foot. It's probably within a decade, some parts of Norfolk and some other cities, particularly along the east coast of the United States, are probably going to have to disband those streets or else do something to keep the ocean from coming in. It's really getting to be a significant problem. This is likely to increase as a problem as the oceans overall continue to increase. On top of that, land is subsiding in much of the U.S., particularly in the eastern half of the U.S., where the subsidence and other factors affecting the amount of sea level means that instead of, by the end of the century, a meter of sea level rise, 3.3 feet, you might see 4, 5, 6 feet of sea level rise in certain areas. They're likely to be pretty significant effects. Not so much in Alaska, where the gravitational effect is actually increasing the land mass, right now at a rate that's higher than sea level rise. But in the future, the increasing acceleration of sea level rise could mean even here, maybe something in the order of a foot by the end of the century. But that's still unclear, because it really depends on just how big the overall sea level rise is. All of these have, all of these kind of impacts I've shown. So far, it's just been pure science. Already apparent in most parts of the United States and affecting important sectors: agriculture, health, water, energy, transportation, et cetera. We're seeing that throughout the United States. We do know that as the temperature increases more, and with the top, this is from an economic analysis actually was done, that looked at different impacts, so agriculture, water resources, forestry, health, et cetera, based on how much temperature change occurred. And the higher the temperature change, the larger the impacts. The more effects you're going to see on humanity and on ecosystems. We do know also that a changing climate exacerbates the stresses and risks we already face. And I'm sorry, I'm taking more time than I should have. We basically have 3 options. We can mitigate, we can reduce emissions of those gases. We can adapt, which means we can be more resilient, we can reduce the adverse impacts on society resulting from climate change, or we can suffer. Right now, we're doing some of all three. What's up for grab is the future mix. Mitigation alone will not be adequate. The changes in climate are just occurring too rapidly, and you cannot eliminate the emissions rapidly enough. Adaptation alone would also be inadequate because climate is changing, temperatures, precipitation events, et cetera, are changing so rapidly that it's hard to adapt fast enough. So we need to realize that we need to do this through risk assessment. We need enough mitigation to avoid the unmanageable and enough adaptation to manage the unavoidable. I do want to leave you with a sense of hope. As I said, this is kind of depressing. Our future does depend on how we act to limit climate change. We need to recognize that adaptation does require a focus on managing risk. But I also believe that we can draw upon our long history as human beings of responding to the changing conditions around us in facing this challenge, and that we can do something about it. If we look at what can we do, about a third of the overall cause of the emissions is because of transportation, a third about from our energy use, and a third from other uses like agriculture and forestry and other things. In our own households, we are emitting based on roughly those kind of things. The food we buy, the energy we use. We can be more efficient in what we do. Even a simple thing like changing from incandescent light bulbs to the new LED light bulbs makes a big difference and really reduces the requirement for energy. A lot of other little things we could do as well. And most importantly, you could send letters and emails to your congressmen and senators and tell them why this is really important. This is something we need to be worried about. A number of studies had looked at various mitigation pathways. Many of them are win-wins, all those on the left, below zero, where we save money by saving energy. Some require new technology, new battery systems, perhaps new ways of doing solar or other renewable energy. But none of them are excessive compared to the potential impacts. There are many ways to adapt by preserving, enhancing green infrastructure, preparing hospitals, transportation systems for heat waves, developing crops that are resistant to some of the changes we expect to see, et cetera, et cetera. Many of these are win-win. I'll leave you tonight with one quote. Sir David King, someone I knew very well, former head of chemistry department at Cambridge University. I met Sir David when he was the science advisor to one of the UK ministers, prime ministers. He was actually the science advisor for two different prime ministers. And a few years ago, Sir David did something that really hit me hard. Climate change is not just the biggest challenge of our time. It may be the biggest challenge of all time. And we need to really take this seriously. Thank you all for listening to me. I appreciate it. And I'd be happy to address any questions you have. There's someone in the back.
Say your name and say your question.
No. There we go.
Yeah, is that better?
Yes.
Yeah, my name's Craig, and earlier on, I don't doubt that you have an explanation for this, but how did you determine the temperature rise over the past 2,000 years? Was it through looking at the Arctic ice or Antarctic ice, or how was that actual temperature
Yeah, I didn't
determination
explain
made?
that very well because I just didn't want to take time, but it's based on a variety of different proxies. Things like the analyses of ice, but it's not just that. It's looking at analysis of ocean sediments, land sediments, tree rings is an important one, analyses of coral reefs, and should you go back in age with coral reefs. There's a whole variety of them all over the northern hemisphere particularly, not as many in the southern hemisphere. They're trying to increase now the number in the southern hemisphere. But these proxies give us a good idea of what temperatures were like over that time period. And these are down to not quite the annual time scale, but close to it. We can actually go back over the last 25,000 years by looking at other records, going back to the end of the last ice age. And it generally appears that, likewise, this period is the warmest on record.
Thank you.
Yes. Yeah, you have to wait for a mic. Sorry about that. She's coming. Eleanor's getting you.
Hi, my name's Elaine Schroeder. Could you tell us or say something about feedback loops and tipping points?
Okay. So in chapter 2, we talk about all the different feedbacks that we understand in the Earth's climate system. And in chapter 15, we talk about potential surprises, which talks about things like what's happening with permafrost, like I mentioned earlier, as being a potential tipping point where things could be suddenly much worse. So feedback's an important one for this area is what's called the ice albedo feedback, where as ice melts, it leaves the land or the ocean open, and that means instead of reflecting more of the sunlight is absorbed and heats up that area more than it would otherwise. So that's a very important feedback. That's why, it's probably the main reason that the Arctic, in fact, there's a big fight in the science community going on right now. Is that the primary reason for the Arctic increasing at twice the rate, or is it because of feedbacks in the circulation patterns from mid-latitudes over the Arctic? And it appears to be somewhat a combination of both. But ice albedo feedback is one of the important feedbacks. One of the other important ones is what's called water vapor feedback. I already mentioned, as the temperature increases, the evaporation rates increase, that puts more water vapor in the atmosphere. Water vapor is also an important greenhouse gas. We used to get accused by the deniers that you guys ignore water vapor and yet it's the most important greenhouse gas. No, we don't ignore it. It's just water vapor is part of the climate system. And so we take its feedback into account. But water vapor feedback is an important thing. Effects on clouds are very important. Overall, we think that the effects on clouds is to warm from the increase in temperature. But there's some important feedback, some of which cause cooling, some of which cause warming in clouds, and we track that very carefully. All the recent analysis show the net effect is likely a warming. There's some other feedbacks I won't get into, but that gives you an idea. Now, there's some other potentially really important tipping points. For example, the decrease in sea ice in the Arctic. We don't exactly know, as it gets to be less and less sea ice, what impact is that going to have not only in the Arctic, but worldwide in terms of affecting weather patterns? Big questions about that. And so we call that a tipping point. It's a thing we don't understand very well, a potential surprise to us. And there's others. What's happening to coral reefs is a big one. Here?
Question about, my name's Tom Wagner. A question about the permafrost. Now, as the permafrost melts, and instead of just little tundra plants, we'll start getting trees and bigger plants up in the Arctic. Does that offset the effect of the rising methane by absorbing more CO2?
It could if there was enough of that. Scientists, this is where you're getting into biology, and as my wife will tell you, that's getting dangerous territory for me. But She's shaking her head, yes. But most biologists think that the melting is likely to cause more emissions than you're going to take in, even if you can grow more other types of plant life in those regions. And I don't know what the possibilities for growing plant life in those regions are.
Sir, what would you, my name is Robert Sewell. What are some of the things that you're most excited about in terms of either technological or social changes that we can do? What turns your crank? What would you recommend for us?
Well, I'm trying to put my money where my mouth is. We're in the process of putting solar on our own house, and we have learned that the payback on that is 12, 15 years or so, and hopefully within our lifetimes we will see, to the point where it's earning money for us. We're not going to pay for energy, for electrical energy, from now on after this is put in this fall. Solar is getting to the point, and wind power is getting to the point where they are so inexpensive compared to other energy sources that it really makes a whole lot of sense to greatly increase the amount of both. One of the analyses I've seen recently suggests that solar and wind power will become cheaper than natural gas as the cheapest forms of energy this year, end of this year, or sometime next year. We already know natural gas is much less expensive than coal, but here we have an impact. If we can go to renewables, whether it's solar, wind power, or perhaps making better use of ocean waves or other sources, as well as geothermal, or even nuclear, they don't cause air pollution, which is the other thing. I developed one of the first air quality models when I was at Lawrence Livermore National Lab. We can largely eliminate air quality problems, air pollution problems, asthma problems. And I think that's kind of exciting. So we can largely solve what's going on with climate change. If we could transition rapidly enough, we're going to slow it down. We're not going to completely prevent it. But we could largely get rid of our air quality problems. And other countries are seeing this too. I get told all the time, oh, China's continuing to build coal-burning power plants. Well, that's stopped. China is now transitioning. In fact, this summer they almost did it too rapidly. They started switching a number of their coal-burning power plants to natural gas, and didn't have enough energy for their people to have air conditioning in Beijing at some points. But they're trying to transition very rapidly, first to natural gas and then to solar and wind power. And they're trying to transition their transportation systems. Their rules for vehicles are much stronger than ours over the next 10 years. And so I think we're starting to see the verge of a revolution in how energy and transportation is done worldwide. And I find that really exciting.
My turn? Hi, John.
Tom.
Thanks for a very good talk. My name is Tom Thornton. I'm the Dean of Arts and Sciences here, and I know you come from a public university that serves your state and its interests. We're in a public university that serves its state and its interests. We want to educate people, and I know you've had an interest in sustainability education, interdisciplinary education. It's clear from your talk that there's been a revolution in scientific understanding of Earth's systems, I think particularly since World War II, through instruments, through interdisciplinary study, through modeling, and so on. We haven't seen the same revolution. It's on the verge, maybe, but on the policy, governance, and response sides. I think it's fair to say that. How do we, or what do you think we need to do to be training people, not just to be climate scientists, but also to be people working in a whole range of industries and sectors to respond to these challenges?
Yeah, I've been personally worried about that myself, and about 10 years ago at Illinois, I led the development of a new school called Earth Society and Environment, where we brought together atmospheric sciences, geology, and geography together. So social sciences from geography, working with physical scientists from geology and atmospheric sciences, and a few hydrologists in geography as well. Could we do something different towards looking at sustainability? And as part of that, I developed a new major at the University of Illinois called Earth, Society, and Environmental Sustainability. I always hesitate because they actually changed the name of it a little bit to bring in the word sustainability after I developed it. It's called ESES. I wanted to develop the easy major, and I couldn't get the acronym right. I just could not get the acronym. Darn. So I came up with ESES. And it's got a couple hundred students in it, plus a whole lot of extra students online with it as well. I think we could have had a whole lot more. A lot of students are interested in it, and it's those students who are now going forward into a variety of different fields as they're graduating. Some go to law school, some go to onto management programs in business and other areas. But they're coming out of there with an idea of being able to look at things interdisciplinarily, and both at the social sciences and the physical sciences in ways that most students don't have that education. I think those kind of programs are going to become really important. On top of that, another way I'm trying to affect things isn't as much education as it is just trying to have an impact, is I'm in the process of leading the development of a new research center at the University of Illinois. It's across the entire University of Illinois system, so it's 3 different university campuses, and it's called Illinois Cures, Illinois Center for Urban Resilience and Environmental Sustainability. And in that center, our aim is we want to be the go-to places for cities to think about their futures. How do we get them dealing with their stresses, the variety of stresses, to be able to take into account climate change looking at the coming decades, along with all the other problems they're facing. And I know that we have the expertise at our 3 campuses, plus with partners. We want to have partners with some other schools. We're already talking with Argonne National Laboratory and Northwestern University and University of Chicago joining us. And we'll probably have other partners as well. We want to do this both for big cities and little cities, and we expect to have a lot more partners from other schools across the nation and perhaps the world. It's really nascent yet. I mean, it's just developing, but I see a high potential need for this if we can do it right. I'd like to get this started, then hopefully turn it over to other faculty and let them run with it. But we'll see what happens.
My name is Laura Haywood, and it seems like the scientific community has done a wonderful job of figuring all this out and projecting what can and will happen. And the failure maybe has been more on the political end and people actually doing anything about this, people who are capable of it. So I kind of tend to think things are going to get a lot worse before they get better because nothing's really happened yet. Science is there, maybe the technology is very possible, but if our political system isn't having it, well, it's not going to get better. So my question is, if things really do go south, and say we do have this 3 degrees centigrade change in temperatures that signifies a huge change, loss of coastal areas, huge weather pattern changes. What I wonder is if at that point people say, okay, no more CO2, we're going to really change. How does our climate rebound? Can the Earth recover once the damage is done? We're still trying to talk about preventing damage, but I want to know, can it rebound if we don't prevent it?
If we could develop geoengineering technology, I'm not a believer that we can develop technology where we can just eliminate the warming by putting up reflections in the stratosphere. I think there's too many problems with that. But perhaps eventually we'll develop technology where we can remove CO2 from the atmosphere or remove it before it gets into the atmosphere from the various emissions we are making. Then we can do something. Otherwise, I already mentioned to you that the carbon dioxide, methane has a very short lifetime, 10 years. A little bit longer, but not much more. Nitrous oxide has about a 100-year lifetime. It's not changing quite as much as methane and CO2. But CO2's second lifetime is thousands of years. And so in 3,000 or 4,000 years, we're still going to have 15% of the CO2 we're putting in the atmosphere left there beyond what was there naturally. So we're leaving a long-term legacy. And that is really a concern. Now, maybe that technology will develop where we can do geoengineering to remove CO2 from the atmosphere. But right now, it's just too expensive. And we have some technology. It's just that's way too expensive. You cannot possibly have enough atmosphere go through a device that, even if you put up thousands of devices, to remove enough to matter. So we got to come up with better technology if that were to occur. But otherwise, we're leaving a long-term legacy, and it's really an issue, really a problem. You know, I do worry. You know, I often will say, you know, we have 3 sons and 5 grandchildren, and I really worry that, you know, 50 years from now, my grandchildren are going to look back and say, "Gosh, I know my dad worked, you know, my grandfather worked on this, but what were they thinking back then?" You know. Because I'm really afraid that we're leaving a tremendous problem to those that come after us.
Hi, I'm Angie, and I'm thinking a lot about water, both freshwater and marine. You know, all of these projections are quite alarming. You know, I grew up as a farm kid in the Midwest too. So we always think about weather and you know, how things are going. But one of the questions that's in the back of my mind is really about both drought patterns, but also water temperature patterns and harmful algal blooms in the future. And I know that might not be your area, but could you touch on it a bit?
Yeah, I don't know an awful lot about algae blooms. I know that's becoming a very important issue in Florida right now, but with the red blooms. But I don't know how likely that is in the future. If that is related to the fact that the oceans are just warming, then maybe that is going to become a big, big problem. But I personally just don't know enough about it. I haven't read enough in the literature, scientific literature, to say that this is going to become, you know, the next big issue. But it's certainly a big issue in Florida right now and growing, and may have a huge impact actually in voting this fall in Florida.
There was a book published in 2015. There was a book published in 2015 about toxicology and fresh and marine events that was pretty alarming.
And it suggests this is going to become more common?
Correct.
Yeah. Okay. I have to add that to my talks, as bad as that is. Yes, and next question? Anybody?
Here.
Oh, I'm sorry.
My name is Dixie Belcher, and I have been reading about something called sustainable agriculture, which is no-plow agriculture, and the idea is that plowing releases carbon into the air, and if you don't plow, you bring carbon in, and it can go down 200 feet and stay there for several hundred years. And these books are quoting scientists, I can't remember what their names are, that if everybody in the world farmed doing this method, that within 10 years, all the excess carbon would be out of the air. Is that true?
I don't think that's true, but it certainly can have an impact, and we're starting to see impacts from that in the Midwest. We have a very close to our house is our University of Illinois farms, and across the street they're growing pumpkins along with corn, with the idea that you're helping hold the soil even more by having this additional life forms in the soil, these additional plants. till agriculture has become much more common in the Midwest. You don't see plowing like you used to at all already. But for that to draw out enough to eliminate the problem, I think that's very unlikely. I thought I had seen analysis that said that just was not likely to happen. It could help. And if we added enough trees and where it was possible to do so, that could certainly help. But none of those will be enough to eliminate more than about a third of the problem.
Hi, my name is Rebecca, and I really appreciate in talks like this always hearing ideas about how we can help with changing our light bulbs and recycling and solar and all that. The one thing I never hear about, and I think it's probably a pretty big taboo issue, but that makes common sense in my head, but I'm not seeing stats about, is how the increasing world population is being both affected by climate change, but also driving climate change. And my question for you is there studies on that?
Yeah.
Where could I see them, and why aren't we talking about it? I know that there's cultural and religious taboo, but I also think it's really important and should be part of the conversation for how we can move forward to mitigating problems for future generations.
No, certainly population is a big driver because that's why we have so much demand for energy and transportation as we do, and for land use change. The United Nations has put out a number of reports about the changes projected in population, and when I show you those projections for the future, that includes population increase estimates in those. We look at a range of different assumptions. That's why there's high cases and lower cases that depend not on population, but also on our choices we make about land use, energy, transportation, et cetera. That's really important. In addition, there are some other choices we make. What food we eat. There is no question, I grew up on a farm, I love eating meat, but I also recognize that the production of cattle and pigs, particularly, tend to lead to a larger use of energy resources than other food choices we make. And so, that is an important factor. I sometimes have a slide where I show all these other factors, but I felt I had time to go into all that tonight.
Yeah, thank you. I would just like to see that being part of the conversation of reducing family sizes as an option for helping to reduce climate change. And I know it's super taboo, but it seems like it's
That's
part
why
of
I
the
stick
equation.
to the science.
You touched on my question a few minutes ago, but people talk about geoengineering and technologies for taking carbon out of the atmosphere, and I was wondering what the role of basic technologies such as a tree can have, like massive reforestation and that sort of thing.
Massive reforestation can certainly have an impact. I wish I knew the numbers in my head for just how much impact that could have. That cannot eliminate the problem, I know that. As some people have implied that. But I don't know exactly, that's why I said something in order of a third. That's kind of what I remember. But I wouldn't want to be held to that because I don't know the number very well. But it would really have to be quite massive in order to achieve that. Anything else? Otherwise, thank you all.
One more question here.
One more
From the
question,
student.
sorry.
Oh my gosh, I got in after the claps. I just was going to ask, so I think it was touched on a little bit earlier by another person, but in the question of like, what can we do? And obviously like personal action, installing solar panels, things like that, trying to reduce your consumption is really important. What public policy are you most excited about? What kind of changes? I mean, I know, again, you're on the
Yes,
science
remember,
side of things.
I worked for President Obama, and essentially almost everything we were trying to do in that direction has now been set aside by presidential orders in the last 2 years, year and a half. So I think it is important to develop policies that promote the transition away. I think it's going to happen anyway, as I was implying. I think the technology is taking us there. But it sure would help if, as a nation, as a planet, we decided that that's what we're going to do, because I think it would make a huge difference and not only help things like climate change, as I said, but also help air pollution problems that are, killing 3 million people around the world. So, thank you again.